Hello there, and welcome to my talk for Sustainable Places 2020, Sustainability at the Software Layer. My name is Chris Adams. I'm one of the directors of the Green Web Foundation, and this talk is online at bit.ly/sust-soft-layer. Okay, if you don't know me, my name is Chris Adams, and I look more or less like this. And I've spent the last 20 years working as a product manager, a developer, and a designer and a user researcher in a string of wacky environmental data-focused startups like Loco2, which was all about trying to get across Europe by train instead of plane, Amy, which was about understanding the carbon footprint of everything and making that available as an API. And these days, the thing that I want to talk to you today is the Green Web Foundation, where I spend a bunch of my time working to make the web green with open source software and open data. If you want to get in touch, my details are below, chris@thegreenwebfoundation.org, and I'm online pretty much everywhere like LinkedIn, Twitter, GitHub, and so on as Mr. Chris Adams. So during my time with you, I'm hoping to cover these three topics here. I'm going to give you an idea of the trends taking place at the software layer, where I tend to live, and also at the energy layer, where I've ended up learning a lot over the last couple of years, and where I think there are a lot of interesting comparisons to be made and patterns that the two of them share. Also, I'm going to talk a little bit about carbon intensity as one of the other levers for carbon reduction, as well as energy efficiency, which is quite common. And finally, I want to share with you a mental model which I use to help think about decarbonizing digital services, which I call GOLD, which stands for green, open, lean, and decentralized. But before I start, I think it's really useful to open, and it's important to open with what should be an uncontroversial and blindingly obvious statement. We are in a climate crisis largely because we keep burning fossil fuels instead of finding a path off them. And I'm really focusing on this finding a path off them part because when we talk only about energy efficiency, it does feel like there's the elephant in the room that we're not really talking about. And when you think about, say, our use of the internet, it's even more pronounced. So every time we use the internet right now, we end up contributing to climate change, largely because it's still powered by fossil fuels mostly. And this is a thing that I work on at the Green Web Foundation, and it feels like a really obvious thing to fix, especially if you realize just how much needs to be changed to face the climate crisis. And yes, you can make the argument that pretty much all economic activity contributes to climate change, but it really feels like this one is more solvable than most. And I hope that by the end of this talk, you'll actually agree with me on this. And we can look forward to the next 10 years of shifting to an entirely fossil-free internet. So what would that look like actually? So I'm going to take a quick whistle-stop tour of how energy markets work. And I need to stress that this is partly because I think it's useful to understand this as a technologist, because the cost of energy makes up such a large part of your cost structure. And I think there are also some trends which it's worth being aware of that you can take advantage of. And I hope that it will also help you realize that this dream of a fossil-free internet is totally something we can realize. Now, I need to preface this. I am speaking as a developer and I don't have that much time. So this will be like a kind of cartoon rather than a really accurate description of all the complexity that comprises energy grids. But I still hope it's useful to you. Okay, so this chart here gives an idea of how kind of markets work. Generally, you have this idea of total system load, which is the amount that we all put onto the grid when we try to use power. And there's a kind of cost for each kilowatt hour of power that we use, which, like markets, follows the law, increases as demand increases. And generally speaking, you might have grid operators whose entire job is to make sure that the amount of power supplied to the grid balances with the amount that we're trying to draw from the grid. And if you don't do that, then bad things happen. It can end up damaging lots of equipment. So what tends to happen is that these grid operators will buy power from the people who generate power, then they'll sell them on to electricity retailers, who then end up selling it to us. And this means that these fluctuations in the cost of power tend not to be exposed to us directly, but it's useful to understand that they're there. And also because different forms of generation have different properties, they sell into the market at different costs, and it's useful to know about this. So, for example, nuclear, on the left-hand side here, it's quite expensive to build, but once it's built, the amount of the cost per unit is actually of every unit of power that they generate is relatively low. And for that reason, they want to sell at kind of high volume, but a low price into the market to make their return. And also, there are some other properties of nuclear which mean it's quite difficult for that to ramp up and down inside a single plant. So that's why they might sell cheaply, but in volume. Now, that's different to, say, coal power, which sells into a market at a higher rate, partly because the marginal cost, like the cost of each extra unit of power from that coal-fired power station, is higher, largely because they have to burn coal for it. And the trade-off is that, say, coal-fired power stations can switch on and off, and they can kind of scale with a bit more ability and with a bit more ease than, say, nuclear, for example. And this means that there are times when they might just not run a power station. So they aren't making money from selling power, but they're not spending money to burn coal either. Then finally, you have fossil gas. So these are like open cycle gas turbines or closed cycle gas turbines. So here, the cost of power is relatively high for them because, but they are able to scale and up and down quite quickly. And this means that they can, for example, just leave a gas-fired power station off a lot of the time, and only turn it on when the cost of electricity is high enough to justify. And they're able to basically be idle a lot of the time and still be profitable because they can sell at such high prices. And this is pretty much how it's been for quite some time. But over the last 30 years, we've seen how the price of solar and wind has basically plummeted, and that's had an impact on how the kind of grid mix works. And the thing about renewables is that the marginal cost for them, because there's no fuel to burn, it's free. But they're only really able to sell power into the grid when it's windy and sunny. And as you'd imagine, if you run, say, a nuclear or coal-fired power plant, this is a bit frustrating because suddenly someone is undercutting you, which means that it's going to be harder for you to sell a lot of the time. And this has some other kind of more subtle effects. So, for example, when you have a very windy day and a sunny day, and you've got more power being fed into the grid, you might say have a scenario where you might switch off fossil gas, and you might switch off coal. But if those have scaled back so far, and you still need to actually reduce the amount of power going into the grid to balance things out, what can you do? Well, we've discussed pricing as one mechanism, but if there's still more energy coming into the grid, then the one thing that an operator can do, and sometimes do, is they will basically pick up the phone to speak to generators in, say, a nuclear plant or a large coal-fired plant, and ask them to scale back their power. Now, when you might do that, this actually has a risk of introducing more wear and tear and possibly damaging the actual power plant that you use. So it's actually it's not unheard of for these operators of these power plants to essentially ask for compensation to scale this power back. And when faced with this, sometimes it's easier for, say, to just change the price of power and reduce it such that you can create incentives for people to use power rather than use more power to balance the grid. And this ends up with us having like negative power prices in some cases. So sometimes it's basically easier and cheaper to pay people to use power than it is to call someone up and turn down their power plant because it's so complicated to do that. And this idea of this is actually useful to be aware of when we think about scenarios where you have things like, say, battery coming onto the grid these days. So we've seen a similar kind of fall in the cost of batteries in the last 10 years that we've seen with things like wind and solar now. And the thing about batteries, like kind of power storage, is that you can fill up on power when the cost of when the cost of power is low, and then you can still sell in to the market when demand is high. So if you have these two systems, you end up having something which feels a bit like a kind of pincer movement from the future when it comes to energy markets. And this ends up totally changing the economics of how we kind of source power. And for this reason, you're seeing a lot of large technology companies investing in renewable. In fact, large technology companies are now the largest corporate purchaser of renewables. And when you see why, one of the reasons is because they see it as a way to reduce their electricity costs, as well as making them look good. So this is one thing I want you to kind of take away, is that we see changes in power, and the cost of power is likely to reduce, largely driven by the introduction of renewables onto the grid. The thing it's worth being aware of is that if you want to be using green power, and you're drawing power from the grid, like we just seen, you don't really have direct control over what comes into the grid a lot of the time. But if you do know how much power is coming into the grid, you can at least account for that. So when people say that they're running on green power, there's a few different ways that people might do that, and I'll refer to that a little bit later. To make this a bit more concrete, I'm going to give an example of how this has looked in the UK. So the UK has been one of the fastest, I think the fastest country in the world to decarbonise in the last 10 years. And this is a map showing the different kinds of power generation on the UK grid. You can see that the grey circles are basically large centralised coal-fired power plants. And this was the story in 2008. So most of the power would be coming from nuclear and coal with a little bit of gas. Now, if we fast forward to 2018, we can see this explosion of these yellow dots, which are represented by solar. And you can also see that these green circles represent a proliferation of, say, wind turbines. And this is how the UK grid has decarbonised as fast as it has. It's basically shifted from a small number of centralized fossil-based generation to a much wider, a much more distributed kind of arrangement with lots and lots of renewables, kind of like how we saw here. And if you look forward, this is what's projected for the UK, is that we'll have even more renewables on the grid and more offshore wind, and also interconnections, so that when there is when there is more power on the grid that's being generated, it's possible to export that or import it from other countries. So this gives an idea of like a trend that we might be aware of, and if you are able to control when you use power, then there are savings that are available to you, which I'm going to touch on a little bit later. So let's compare this to how you might provision infrastructure as a technologist. So we have a similar kind of approach, or you can take this idea for thinking about how you might provision the servers and the services to run an application, for example. If you think of, say, bare metal servers as an expensive upfront thing that makes sense if you're using it all the time, you can think of it in similar terms to stuff like, say, nuclear. And likewise, for things like virtual private servers, they're a bit pricier for the same performance, but you can spin them up and down the same way we might have done so with coal or gas. Now, more recently, you're seeing things like, say, Heroku as an example of a platform as a service, where scaling is much easier than working with a virtual private service, but you pay a higher price. And then finally, you might have things like functions as a service, otherwise known as serverless. Now, these things here are more expensive per unit, but because you only pay per request, the total cost can be lower. And when we think about a typical kind of software as a service solution that might be used between two businesses, it's worth it might change how you actually decide to provision that. So this is an example from who is now I think one of the principal vice presidents of cloud at Amazon, Amazon Web Services, Adrian Cockcroft. So he says many workloads are spiky and drop to zero for extended periods, and typically applications might be used 40 out of 168 hours in a week. So that means that 75% of the time we have computers running idle, which means they're burning money and burning fossil fuels a lot of the time for little utility. And if you are, and this is partly why you see a shift towards technologies like, say, the Jamstack, for example, where you might serve static files, which are cheap and easy to serve, and only really run compute at using something like a serverless approach for the time you're using it, rather than have lots and lots of idle tin running. And I think it's worth, at this point here, bearing in mind or looking at how other fields in technology have basically tried to kind of shape the market, I suppose, or shape the way that we might build digital services and design them. And it's worth looking at, I think, the accessibility movement, because some of the things they're doing, I think that we are seeing in our field when it comes to like sustainable technology now. So POUR is a kind of mnemonic which stands for perceivable, operable, usable, and robust. And these principles are key to something called the WCAG, which are the Web Content Accessibility Guidelines. Now, any public sector website that is available to the public needs to comply with these now as a kind of matter of law. And these principles are a way of kind of checking if a website is actually accessible to a wider audience, especially with one with, say, accessibility needs. So perceivable is the idea that if someone might be partially sighted, there are still ways to actually see this. So it might be readable through a text reader or something like that. Operable was the idea that you can interact with the website using more than just a mouse and keyboard. So if you don't have strong motor skills, undo features might be really useful for you. And this is an idea behind operable. Usable would be the idea that you can understand what the actual interface is asking you to do. And if you might be, say, neurodiverse or not specialized in a particular language, then you can still make use of it. And then the final one is robust, with the idea being that a site should kind of degrade gracefully. And if you've ever been in a scenario where you're waiting for a website to load a huge kind of payload of JavaScript where on your phone, you'll appreciate how useful it can be to just have a text-only version of the same application. And these ideas of POUR are often used in development now as a kind of way to help developers kind of memorize what they should be doing and check against this. And this idea of POUR has kind of become adopted increasingly when it comes to building websites for the public sector, and we've now seen this in the private sector. So around about this time last year, we saw the first ever kind of Supreme Court victory where a private sector website was sued because they hadn't designed with these principles in mind. And I think you're likely to see something like this when it comes to the choice of power and the carbon footprint of websites. And this is an example of this. So on the 10th of September this year, we saw the new strategy released by the UK, what they intend to do with digital services. And they are looking to do something like this with the environmental impact of the digital services that they use now. And you can read through this, but I've saved you the effort of doing that. And the thing you can see is the appendix on their report and what they've explicitly said they need to have where from any services they purchase from suppliers now. They want to be able to see that things are running on renewable power, and there is a clear transparency for this. And the UK government has to do this because they have legally binding targets to reach net zero. But any large company that has anything like a science-based target to hit net zero, as in zero emissions by, say, 2050 or earlier, they will have to be doing this too because they need to understand their own supply chain. So we're going to see more of this. And with this in mind, this is why I've kind of shared this idea of GOLD, which is a little bit like POUR, but for designing for low carbon infrastructure or carbon aware design. So the phrase GOLD stands for green, open, lean, and distributed. And I'll run through these in a bit more detail to give you an idea of what this might look like. So green stands for green energy and low carbon power, as you might expect. And let's come back to this kind of idea of a stack here, where we know that if we're getting power from the grid, there's going to be some kind of fossil power which we need to account for, even if we know that the other parts of the grid are actually getting greener over time, as we've seen. Now, there's one approach that you can take, which is basically to just pay for offsets for the carbon emissions for the kind of fossil fuel parts of the grid power that you use. This is actually easier than trying to get your head around the energy markets that we just spoke about, and I need to stress that my description is a very, very high level, high speed version. It's much more complicated than this. And this is very popular, but you can argue that this might not be solving the problem. And there is, in many cases, there is an idea of additionality that is worth taking into account here. Like, is this actually solving the problem? Are we doing anything about changing how the grid works? And this is actually a thing that we see. Another approach, which I think is more satisfying, is this idea of basically accounting for the power you use and kind of topping up. So for the green power that for the non-green power that you're using, you put as much power into the grid as you pulled out. And this is a little bit like you only using green power now, because in total, you can make an argument that you're now using entirely green power. The only problem is, though, is that, as we know, renewables are variable. So they might not run at night or when it's not so windy. And even if you're a $1 trillion company like Google, they are not able to do this right now. And this is a chart that they've actually shared from some of their own kind of carbon-free papers, showing how they have a relatively static load profile for data centers, and the amount of energy might be different over the grid. So there will be times when there is less energy on the grid, even when they account for grid intensity and the power they've purchased to do this. And this actually is a solvable problem, because we now are seeing things like battery coming onto the grid, battery power coming onto the grid, and just a proliferation of renewables, which mean that even when you have some of them not providing power all the time, the total amount is greater than what we had before. And Google, when they shared the report for this, they basically said they think they can run all their infrastructure on entirely green power by 2030. So this gives us an idea that yes, this definitely can happen. It's just something we don't have right now. So open. I spoke about green. Now let's talk about open in terms of a quality of digital services we might want to have. Now, I talk about open data and open source. When we talk about open data, one of the good examples is Electricity Map. So if you are curious about the carbon intensity of power and what kind of grid mix is feeding into any regions in the world, the Electricity Map team, what they do is they take all the open data that's published by every government they can find, and they make it accessible in an API so that you can pretty much see where the grid intensity of various parts of the world. So France, for example, has loads of nukes, and as a result, it has very, very green power by comparison, or at least low carbon power. Now, Germany, where I live, is the land of solar and coal, so it's actually more carbon intensive. And Poland, where there is a massive coal industry and a really entrenched industry, no less, you'll see that the carbon intensity is quite a bit higher. And this changes over time, and you can actually subscribe to an API to see and get an idea of when this might change. So I spoke about open data, and this is actually some of the stuff that's powering the work that Google has been doing recently. Google have started to be a lot more open about how they power their data centers, and they've introduced this idea of a carbon clock to show which parts of the day are running on green power versus not running on green power. And over the next, say, 5 to 10 years, the goal is to make all these clocks turn entirely green. But if you know how much power you're using, and the grid mix of the power you draw from the grid, and how much power you're generating, green power that's being generated, you can come up with kind of carbon clocks of your own. And if this is interesting to you, I'd really like to talk to you about this, because this is an open approach which I think is absolutely replicable with any other provider that is prepared to share this level of transparency. So we spoke about green and open. Now let's talk about lean, making the carbon you emit count, because we cannot just because of the design of the internet means that even if we run on green power ourselves, the fact that data has to hop through an entire network means there's going to be a carbon footprint associated. And one way you can quickly check for this to get an idea is looking at a website called Website Carbon by the agency Whole Grain Digital. You can put any website in here and you'll get an idea of what the carbon footprint of that website will be by looking at how much data is sent over the wire. Now, this uses data from the Green Web Foundation that I help or run, which decides which basically provides information about whether a website is running on green energy or not. But as I said before, there is still there is still fossil fuels from basically shifting data over the wire. But there are tools that you can use to improve websites to optimize for this. One example is Coach by the organization SiteSpeed, which will basically analyze your website and give you an idea of what things you might need to change to get a higher score, so you can basically feel better about yourself and look better about yourself. And we did some work with the team at SiteSpeed to build a sustainable web plugin, which lets you work out the carbon footprint of these pages and gives you some directed guidance based on how a site has been built. And these kinds of ideas have actually been adopted by other organizations now and other services. So one example is Cabin, which is a privacy-protecting, carbon-calculating web analytics service that you might use instead of Google Analytics, for example. They will give you a running total of the carbon emissions from a website, and also they'll tell you which pages are the culprits. So in my example, I can see that the news page that on our website we need to fix. It's colossal, way bigger than it needs to be. So that's one thing you might do at a website point of view, but if you run servers, what can you do? So the biggest thing to do is related to how you provision computing. And generally, when you have to match the supply of compute to demand for compute, you have three kind of options. So one option, if you are getting more demand, is to basically scale up, use a larger server. The downside of this is that when you're not meeting that demand, you end up having a lower utilization and wasting a lot more power. The other option is scale out, which has been popularized by companies like Google and other large kind of cloud giants, where you basically design a system such that you can add more servers rather than have a bigger server. And the final one is scale in, which is basically newer, I would say, and it's largely around taking an existing API that a computer will use or a program will use, and plugging in something which uses the same API to let you do the same amount of work, but more efficiently or faster. And I'll give some examples of this shortly. So let's talk a little bit about scale out just to provide a bit more perspective on this. So when we have switched to having one large computer to a system comprised of lots of small computers, we've ended up learning how to manage lots and lots of small machines. And we now see there are increasingly services that you might use which allow you to basically match the jobs that you're running, the different kind of services, to the infrastructure so that you don't need to use so much of it, which increases utilization and saves you a bunch of cash. This example is from a piece of software called Nomad, which is used by a number of large providers, and it's generally seen as one of the competitors to something like, say, Kubernetes, which is a very common tool for managing, say, containerized workloads or smaller sets of programs now. Another option, and on the subject of Kubernetes, there is a load of really interesting work taking place in this field. There are groups. There's a company called Edgetic now, and what they do is they allow you to optimize an existing cluster of Kubernetes machines, so that you are able to scale down the infrastructure, scale down the services, scale down the kind of hardware that is not in use by basically shifting bin packing the jobs that you are running onto onto a smaller number of machines. Now this ends up providing a measurable power savings, and this idea of like scaling out is actually pretty much what, if we look back at the energy system, is how France manages its nuclear power fleet. Because we know it's difficult to scale them up and down, France literally just switches some of these power plants off entirely sometimes. But I digress. So this is the idea of scale out. Now, scale in is a more recent approach, which I think is really interesting. And you can see a couple of good examples. So Scylla DB is one example of this. There is a very common tool called Apache Cassandra, which is used in by a large number of companies who basically use NoSQL to manage kind of big data style workloads. What these folks have done is take the software and then re-implement it in a language which is slightly faster with a series of newer ideas, and they've then provided a API to basically allow you to run this instead of, say, Amazon DynamoDB, which might be the other competitor to Cassandra. So what they've done, so this is an example of taking some software and then providing a API compatible equivalent so that you can use less infrastructure to do the same kind of work. And if you work with SQL, you can see this as an example with Swarm64. Swarm64 do this for Postgres, which is a very popular open source database. And a good example of them using this is using Swarm64 to manage wind turbines. There's a company called Turbit that does this, and there is a white paper where they talk about how their use of this allowed them to stay using SQL, which is what they had competency with, against a number of other NoSQL tools. And the reason they can do this is that they have the same API that you might use for writing, say, SQL, but under the hood, they're actually using kind of custom silicon, something called an FPGA, which is a field programmable gate array, to basically reconfigure the actual silicon itself to match the job and match the workload better as it comes through. And this is an example of scaling. Now, finally, distributed is the last thing I'm going to touch on. You can basically move the work you're doing either through to different parts of the world, like we saw with the electricity map, to optimize for carbon intensity, or through time to avoid carbon emissions. So I won't dwell too much on why it's useful to run a data center somewhere where it's cold or where there's lots of renewable power to reduce carbon emissions. But the time one I think is interesting and probably more novel. So this is a screenshot from a website called principles.green, which was created by a man, Asim Hussain, who is who's the head of green cloud advocacy at Microsoft, who are building out an entire sustainable software kind of practice and sustainable software engineering practice. And this is very much the idea of shifting demand so that you can, because some of the jobs you're doing aren't actually, some of them may be important, but they're not necessarily urgent. And if you can control this, then you can basically take advantage of some of the kind of volatility of the price of power on the grid. And I've recently been working with a team to kind of demonstrate this idea in a new magazine. So there is a magazine called Branch, which is all about, say, digital culture and sustainability. And we've taken these ideas to basically surface grid intensity and take advantage of this. So when there are lots of renewables on the grid, we might show the version on the left-hand side, which is a kind of green, high-resolution, rich experience. And then instead, on the right-hand side, when we have lots of fossil fuels on the grid, we'll serve a more minimal version of the same site. So you can still click on an image to see what it is, but we'll send less data over the wire. And I think that this idea of a grid-responsive, carbon-aware approach to design is only going to become more popular, and we're seeing more examples of this now. And I spoke before about the economics of this, and there are reasons for this, because I think in many ways, if you can take advantage of moving jobs around, then the economics can make it possible to do things that you wouldn't have done before. And the kind of jargon term of this is the duck curve. So when there's more power on the grid than can be used, grid operators will often resort to negative pricing to basically incentivize the use of power. And I think that if you can maybe switch jobs on when power is low or negative, then you end up with things making sense that didn't make sense before. And this is you can see this being exposed to customers, like consumers, with companies like Octopus Energy, who have an agile tariff where you'll be paid, as you can see, to use power at certain times. So if you can schedule charging of a car or running a washing machine, then it's kind of in your favor. And this is essentially what Google do when they with some of their work, which is why they are so confident about getting to net zero by 2030. If you are able to break this assumption that data centers have standard load all the time, but instead you can make that match the amount of renewables on the grid, then yes, it can be greener, but also you can actually access the savings that you wouldn't have had before. So this is the idea. So in summary, I think these are things that I'd like you to take away. So we have more levers to carbon reduction than just energy efficiency, like carbon intensity. If you want to think about greening your infrastructure, then think about gold, green, open, lean, and distributed. And there are lots and lots of patterns at the software layer that let you take advantage of changes at the energy layer. And I think this is the main thing I'd like you to leave, to take away with you. So thank you for your attention. My name is Chris. This is how to get in touch with me. And I'm Mr. Chris Adams on Twitter or LinkedIn or anything like that. Thanks, folks, and have a lovely conference.